In this module of Chapter 3 on mortality, Module 3.6, I will cover the concepts and models of demographic heterogeneity. An implicit assumption in the mortality models presented earlier is that all individuals at birth experience the same probability of survival at each age. This assumption is virtually always violated because there are a wide variety of factors that can have profound effects on the risks of death, including within-group differences in genetic endowment or in developmental conditions. As populations age, the composition of individuals in the population changes and they become more selected. Over time, members of sub-cohorts with higher death rates will die out in greater numbers than will the members of sub-cohorts who experience lower death rates. The concept of subgroups endowed with different levels of frailty is referred to as demographic heterogeneity. The winnowing process as the cohort ages is referred to as demographic selection. Suppose we begin with a cohort or basket of fruit consisting of equal numbers of apples and oranges, but that oranges are selectively removed at a higher rate than apples. Clearly, over time, the composition of this fruit basket cohort initially becomes skewed towards apples until finally it is 100% apples. Thus, the differential rate of removal shapes the composition. And in turn, the composition shapes the overall rate of selection. This same effect occurs when a cohort consists of sub-cohorts of different frailty levels. This graph shows age on x-axis and mortality on the y-axis with 4 different mortality schedules for each of 4 different sub-cohorts, including robust, standard, weak, and extremely frail, from the lowest to highest mortality respectively. The actuarial consequences of a cohort consisting of sub-cohorts with different levels of frailty is that the mortality trajectory of the whole cohort will change with the change in cohort heterogeneity. As a consequence, the mortality trajectory of the cohort as a whole may depart substantially from the Gompertz mortality rates, even though each of the sub-cohorts is subject to Gompertz rates. Those individuals with the greatest frailty will die off first, leaving progressively fewer of them in the cohort, and thus altering the trajectory of mortality for the remaining survivors in the cohort. The concept of sub-cohort variance in the risk of death and its actuarial consequences was introduced to the literature 4 decades ago by James Vappell and his colleagues in 1979. These demographers illustrated their concept with the following set of graphs with 2 sub-cohorts subject to different mortality rates, mu1 and mu2, with the dashed line depicting the mortality trajectory of the overall cohort due to compositional changes within it. This graph shows constant sub-cohort rates but decreasing overall cohort mortality. This one constant and one increasing sub-cohort results in decreasing, then increasing overall cohort mortality. Here we have both increasing at different rates produces increasing cohort mortality with a transition between increasing rates. Here's 2 level produces a gradual shift from higher to lower. And here is one increasing rapidly and another near 0 produces a rapidly increasing and then a rapidly decreasing overall cohort mortality. The carry-away message here is that the internal frailty composition and the numbers within each sub-cohort can have profound effects on the mortality dynamics of the whole cohort of which they are a part. Here I will describe the derivation of a frailty model presented in Vappell and his colleagues' original paper. The frailty parameter Z is defined according to the relationship where an individual with a frailty parameter of Z equal 1 is a standard individual. This means that an individual with a frailty of 2 is twice as likely to die at any particular age and time, and an individual with frailty of 1/2 is 1/2 as likely to die relative to the standard. For simplicity, I dropped the subscripts and arguments so that the previous equation is reduced to mu z equal z star mu. Let S be the probability that an individual will survive to age X, and H denote the cumulative hazard function through age X. Then S equal exponent raised to the minus H. It follows that S is a function of Z equal S raised to the Z power. So if S to the Z is survival, and the standard individual Z equal 1 has S equal 0.5 probability of survival, then survival over 6 levels of frailty, or Z values, are given as with Z equal 1/3, survival equal 0.79, Z equal 1/2, survival equal 0.71, Z equal 1 equal the standard, survival equal 0.5, Z equal 2, survival equal 0.25, and Z equal 3, survival equal 0.125, with a mean survival of 0.48. Both frailty levels and initial numbers of each of the sub-cohorts determines the cohort mortality trajectory overall. So again, we have survival for Z equal 1/3, 1/2, 1, 2, and 3 from least to most frail. Then if a cohort consists of equal initial numbers of individuals in each of 5 sub-cohorts, in this case 3,000 each, the average survival for the cohort as a whole is S equals 0.475. If alternatively the initial numbers are N equal 1,000, 2,000, 3,000, 4,000, and 5,000 for the least to the most frail group respectively, then the mean survival is S equals 0.36 because the most frail subcohorts constitute substantial proportions of the cohort. On the other hand, if the initial numbers are reversed, such that N equal 5,000, 4,000, 3,000, 2,000, and 1,000 for the least to the most frail subcohort respectively, then mean survival is S equals 0.6, since now the subcohort proportions are skewed towards the less frail. In other words, higher survival overall. Vappel and his colleagues assumed that frailty at birth is gamma distributed, where lambda and k are the parameters of the distribution. The mean and variance are given by these respective equations. They chose this distribution because it is analytically tractable and readily computable, noting that it is a flexible distribution that takes on a variety of shapes as k varies. The concept of demographic selection resulting from demographic heterogeneity is illustrated with a hypothetical 2 subcohort example applied to the fruit fly Drosophila melanogaster. Using Gompertzian mortality rates for each of the 2 subcohorts with differences in the rate parameter b, and starting with a 10-fold difference in initial numbers in the overall cohort. The effect of selection is shown here. The overall cohort mortality rate closely tracks that for the subcohort with the highest mortality rate, subcohort A, and because of its higher initial numbers, continues through 50 days. At this age, the mortality of the whole, the dashed line, differs only slightly from mortality in subcohort A. However, by age 65 to 70 days, roughly the same number of survivors remain in each subcohort, and thus the composite mortality rate begins to bend towards that for subcohort B. With few survivors remaining of the high mortality subcohort A still living, the overall mortality converges to the mortality of the low mortality subcohort B. At this point, the average mortality slows and begins to decrease even though mortality in both subcohorts continues to increase through all ages. Another example application of frailty modeling is a model developed by James Vappel and myself, describing the increase and decrease of observed mortality as the result of 12 subcohorts, each subject to Gompert's mortality rates, but each in different initial proportions and with different frailty levels. Note in the second column the frailty level from 3.7 to less than 10 to the minus 9. Expectation of life from less than 5 days for the most frail to over 100 days for the least frail, that is the most robust, and the proportions from around 40% for the most frail to less than 1 in 10,000 for the least frail. Here's a graph of Medfly mortality with age in days at the x-axis and the age-specific mortality on the y-axis. The solid line represents observed mortality in this 1.2 million Medfly cohort. The dashed line is the output of the heterogeneity model using the 12 sub-cohorts at different frailty levels and in different initial proportions. These results provide one explanation for the ascending and then descending mortality pattern. Extreme heterogeneity and frailty levels within the million fly cohort used in the study. So overall, heterogeneity modeling yields 4 major insights into the nature of mortality and its demographic consequences. These 4 are taken from Vappel et al. 1979. First, the mortality for individuals may increase faster with age than the observed mortality rates for cohorts. This is because as death selectively removes individuals with high frailty, the average frailty of a cohort decreases. Second, the life expectancy of those lives may be saved by some health intervention, may be less than currently estimated. This is because measures of progress consider only changes in cohort mortality and do not recognize that the proportion of cohorts that reach a particular age has been increasing. Third, past progress against mortality may be underestimated, and as a consequence, predictions of future progress against mortality may be too low. Finally, heterogeneity and frailty may be a factor in observed declines and reversals with age of mortality differentials between pairs of populations. So this concludes this module on demographic heterogeneity.